Everyone, welcome to the next installment of the ITI CRI CREDC webinar series. I'm Randy Sandone, the Executive Director of CRI. Delighted to be here to introduce today's talk, which is multi-receiver GPS spoofing detection for PMU timing verification using a hybrid communication network. A nice, wordy, long, academic research title, and a very interesting presentation as well. I think we're all familiar with GPS. We rely on GPS when we get on that commercial airliner to fly to a distant city because that airliner uses GPS for navigation. We then again rely on it as we get into that Uber at the airport to take us to the hotel, and then once again we'll rely on it on our smartphone as we look for a route to that sushi restaurant that we're looking for in that strange city. Well, it turns out there's a myriad of other applications for GPS, the Global Positioning System, and one of them I didn't know about until I learned about this very fascinating program, this research project, and that is the smart grid. The smart grid relies on these devices called phasor measurement units, or PMUs, which are used to monitor the power grid state in real time by synchronizing measurements across the network. These PMUs rely on precise timing, which they get from the GPS satellite constellation. However, because they use the civilian side of the GPS signal, which is susceptible to spoofing, the signals could be spoofed and interrupted and cause significant havoc in the electric grid system. So Professor Grace Gao secured a research project to identify a solution that would allow us to detect the spoofing of these GPS signals in the smart grid, and that is the subject of today's talk. The speakers are Sriramya Bamidipati, who is a doctoral student in the Aerospace Engineering Department here at the University of Illinois. She received her Master's of Science degree in Aerospace Engineering from University of Illinois, and a bachelor's with honors in Aerospace Engineering and a minor in Systems and Controls Engineering from the Indian Institute of Technology in Bombay, India. Also speaking today is her colleague, Tara Yasmin Mina, who is a graduate student in the Electrical and Computer Engineering Department here at the University of Illinois. Tara received her BS with honors in Electrical Engineering from Iowa State University in 2017. And as I indicated earlier, both Sriramya and Tara are advised by Dr. Grace Gao, who's the assistant professor in aerospace engineering here at the University of Illinois. Professor Gao's research focuses on GPS, GNSS-based positioning, navigation, and timing with applications to manned and unmanned aerial vehicles, robotics, and power systems. I'd like to turn it over now to Sriramya and Tara. Thank you very much.
Thank you for the introduction. My name is Tara Mina, and I'll be presenting our work on GPS spoofing detection via a multi-receiver hybrid communication network for power grid timing verification. So currently, there's a major initiative to modernize the U.S. power grid to establish the future smart grid, which will automatically control the power flow through the electric grid and stabilize the network in real time to reduce the number of failures or large-scale blackouts. And to make responsive decisions in real time, the state of the power grid must be continuously monitored. As part of the modernization process is to install a relatively dense network of monitoring devices across the continent. So in the past decade, nearly 3,000 devices called phasor measurement units, or PMUs, have been installed at critical power grid substations, which establishing a widely dispersed real-time monitoring network. And PMUs are devices which measure voltage and current phasors and provide each measurement with a precise timestamp using GPS, thus synchronizing these measurements across the network with a common timing reference. And any timing inaccuracies can induce a generator to trip, as shown in Daniel Shepard's work. When a generator trips at a critical substation, the resulting additional load placed on the neighboring stations could potentially induce these generators to trip as well. And this could potentially lead to a cascading failure and a large-scale blackout similar to the Northeastern blackout of 2003. So only when these measurements are synchronized can the state of the power grid be reliably estimated. Thus, any vulnerability in the timing provided by GPS corresponds to a vulnerability in the overall system. So before discussing our work, I wanted to first explain some details about GPS and how it works as a navigation system. GPS, or the Global Positioning System, currently consists of 31 satellites orbiting the Earth at an altitude of about 20,200 kilometers, which is a semi-synchronous orbit with a period of about 12 hours. And the key to making GPS navigation work is precise timing. In fact, the system is really just a bunch of very precise clocks traveling through space. As a result, each satellite carries several atomic clocks and continuously broadcasts precisely timed signals to Earth by which users like us can use to navigate. So how exactly does GPS enable us to navigate? Well, each satellite sends a signal toward Earth, where each individual data bit is sent at a precise time according to the atomic clocks on board the satellite. Thus, from the signal, the user not only receives information from the data sent through the transmission, but the user also obtains the exact time that the signal was transmitted from the satellite. And this corresponds to the time of transmission, or the T sub tx in the slides. And on Earth, the moment that the satellite signal reaches your receiver, the GPS receiver chip immediately notes the time at which this signal was received according to its own local oscillators. And this received time is denoted as T sub Rx in the slides. Thus, by finding the difference between the signal's time of transmission with the time of receival on Earth, and assuming that the signal is traveling at the speed of light, we can compute our distance from the satellite. Except not quite. Because the issue is your receiver's local oscillators are not very accurate. Indeed, unlike the satellites, we don't have high precision atomic clocks in our GPS receiver. So the receive time we measure, the T sub Rx, is also inaccurate. And any small timing error leads to a huge difference when the signal is traveling at the speed of light. So if we rephrase, from the user's receive time, we can very roughly approximate the distance from the satellite. And so we remove the equality in the expression. And the approximation of the distance based on the receiver's local clock is called the pseudo range, where the pseudo comes because the receiver's clock, because of the receiver clock error, making this quantity different from the true range between you and the satellite. So in order to determine the true range, we need to determine an extra parameter, which is the error in our receiver clock, or the receiver clock bias. And with this added term, the pseudo range is corrected, and we can obtain a much better estimate of our true distance from the satellite. So as a result, there's actually 4 unknowns that we need to solve to navigate with GPS: our 3D position as well as our clock bias. And to solve these unknowns, we correspondingly require 4 equations, or at least 4 satellites in view, which is definitely not an issue today because of the satellites currently in orbit. You at least see 6 or more if you have open sky view. So for each visible satellite, we have the corresponding pseudo-range measurement relating our 4 unknowns, and with a system of equations for the number of satellites in view, we can use iterative techniques to solve for the unknown parameters, such as the Newton-Raphson method. Thus, GPS not only gives us our position, but also the exact time, and it gives it it's a very precise time as well, to the sub-microsecond level with respect to UTC. Now, GPS is a powerful system, but it also has vulnerabilities. First of all, the all commercially available GPS receivers utilize the civilian GPS signal L1CA, which has a center frequency of 1.57542 megahertz and a bandwidth of about 2 megahertz, or 1.57542 gigahertz. And similarly, the power grid network, which is a non-military application, also only has access to the civilian signals. And there's many advantages to using GPS for the power grid network, including the widespread coverage and its sub-microsecond level timing accuracy. However, and one advantage is that it is freely available and relatively inexpensive. However, this also poses a disadvantage because the civilian signal is an open, publicly available signal with a well-known structure. An attacker can forge a GPS signal to induce a false position, or more importantly for the power grid network, a false timing solution. And this type of attack is called GPS spoofing. And it's especially concerned for the power grid network where timing synchronization is critical to maintaining an accurate estimate of the power grid state. So although we don't have access to the more secure military signals, we can still use them to improve our GPS security. Orthogonal to the civilian L1CA signal are the military PY codes, which are encrypted and thus they cannot be generated by a spoofer. As a result, this quadrature phase signal component establishes a type of signature in the background of all authentic GPS signals. And as proposed and demonstrated in the work done by Sherman Lowe and Mark Psyche, the presence of the signal can be verified without knowledge of the precise bit sequence by comparing conditioned GPS signal samples with that of another GPS reference station. And using the encrypted codes in this way in our prior work, we've shown that we can authenticate a handful of receivers by comparing their received GPS signals. In addition, we've demonstrated the ability to detect a spoofing attack using a centralized framework approach. For a small number of receivers, we can utilize a simpler framework with a centralized processing station, such as this one, where each receiver in the network sends its data to a central processing station, which then sends a corresponding spoofing decision back to each of the receivers. However, for the power grid network with nearly 3,000 devices widely dispersed across the continent, we need a more suitable architecture. As a result, the key objectives of our research are to first utilize the existing power grid resources to develop a multi-receiver spoofing detection architecture, and in order to authenticate each PMU in a coordinated manner. Additionally, we hope to further consider the potential for a coordinated spoofing attack against collections of receivers within the network. And finally, we test our algorithm with data collected during a government-sponsored live sky spoofing event, demonstrating that our algorithm can successfully evaluate the authenticity of each receiver during a real-world spoofing attack. So first I'll explain the proposed multi-receiver communication architecture before discussing the details of the algorithm. Then I'll describe some implementation details for incorporating the system in the power grid network. And finally, we'll conclude with our experimental results and summarize our work. So one standardized communication structure proposed by the North American Synchrophaser Initiative is called NASPyNet. And this is a communication structure which allows for the transfer of PMU data throughout the power grid network. And as you can see in this figure, NASPyNet is divided into several utility subregions, each of which has a collection of PMU devices and a central processing station, which is usually a phaser data concentrator or a PDC. And the PDC performs several key tasks when receiving the PMU data, all of which relate to the goal of monitoring and sustaining the health of the power grid. And each of these subnetworks is connected in a distributed manner via the NASPyNet data bus. In this way, data exchange is available between any two nodes within the power grid network. However, most of the available bandwidth and communication resources are prioritized for data transfer within the individual regional utility subnetworks. So our proposed hybrid architecture will overlay the NASPnet communication structure. Thus, we'll have a widely distributed network of central processing stations, which are usually phaser data concentrators or PDCs, each of which branches out in a centralized manner to a regional collection of PMU devices. Thus, GPS signal fragments can be initially compared and checked within the regional subnetwork, where communication resources are more abundant. Then each regional network can compare a condensed version of its received signals with the other more distant network sites for verification. In this high-level diagram of our algorithm, we focus in on the processes performed by a single PDC. In the regional network, each PMU sends its raw GPS signal samples along with the signal tracking parameters to the phaser data concentrator. And the GPS signal corresponds to a particular satellite time of transmission, which is determined during scalar tracking. And in this way, the GPS signal fragments are already pre-aligned according to this time of transmission when arriving at the PDC. And this significantly helps with faster peak detection, as we see in the upcoming slides. Additionally, each PMU, when it sends, it also sends its signal tracking parameters with which the PDC performs signal conditioning in order to extract the quadrature phase signal component where the military encrypted keys lie. Then the PDC performs cross correlations between each pair of signal samples and computes the preliminary spoofing decision. And it computes this decision for each receiver, and this decision is based on the receivers only within the regional network. Next, the PDC will compare its received signal with those from more distant networks in order to verify the preliminary spoofing decision. And this step is particularly valuable in the case of a more sophisticated, coordinated spoofing attack. And to reduce the bandwidth and processing requirements for this step, the PDC generates a regionally representative signal sample and sends this out through the NASPnet data bus to the distant network sites. And upon receiving data from the distant sites, the PDC compares these signals with its representative sample and computes the final spoofing decision, which is then returned to each PMU in the local network. So now I'll describe the details of the spoofing detection algorithm performed at each PDC, starting with how we perform a pairwise check between any two given receivers within the network. So this is a plot of a quadrature phase correlation between two authentic receivers. One is in Colorado, another is in Ohio for PRN 22. And a quick note, the PRN number is essentially a satellite ID number. So it refers to a particular GPS satellite signal. And in this example, the satellite PRN 22 was at an elevation of about 71 degrees at the Colorado site and about 51 degrees at the Ohio site. And this plot represents a typical cross-correlation result we observe when the received GPS signals are authentic. As you can see, there's a single large correlation peak at near zero lag. This indicates that there's a strong signal match in the quadrature phase channel where the encrypted military signals lie. So also notice that the correlation peak is centered without any additional alignment performed by the PDC, since the signal snippets correspond to a particular time of transmission. Thus, in this way, the PDC can quickly seek the correlation peak within a narrow window from the center. Now, similarly in this plot, we have a typical cross-correlation result when one of the receivers is spoofed. As you can see, the cross-correlation consists only of noisy data points with no correlation peak that lies significantly above the noise floor. And this indicates that the Western receiver, which in this case is spoofed, has a poor signal match with the quadrature phase channel in the quadrature phase channel with the Ohio receiver. And we'll now seek to better characterize the cross-correlation result between a pair of receivers. So we can model the correlation peak result as being from one of two possible distributions corresponding to whether the signal is authentic or whether it's spoofed. If the received GPS signal is authentic, the correlation result can be represented as a random variable having a Gaussian distribution with a large positive mean indicated by mu. And if the signal otherwise is spoofed, the correlation can be represented as white zero mean Gaussian noise. For each correlation result, we develop a pairwise statistic to represent the amount of signal matching between two receivers for a given satellite signal. And the pairwise statistic, which is denoted here as gamma, it's made up of the thresholded correlation result as well as a weight parameter. And the correlation result, for the correlation result, it's compared to a pairwise threshold indicated by tau. If the correlation is above the threshold, the correlation value itself is used. Otherwise, the value is set to 0. And then similarly, the weight parameter also scales this pairwise statistic according to additional factors which may influence the correlation, including the signal quality at the two receivers and the reliability of the receivers. Going more in depth, after conditioning and performing the pairwise cross correlations for each correlation result, the PDC computes the pairwise statistic as shown in the previous slide. And the pairwise statistics are then aggregated for each PRN and then again for each receiver to compute the preliminary spoofing statistic. If the statistic is above the preliminary threshold, we initially conclude that the receiver's signal is authentic. Otherwise, we conclude that it's spoofed. From the signal fragments preliminarily determined to be authentic, the PDC creates a representative signal sample for each PRN, which is created by finally aligning the authentic signals to the nearest sample and then performing a weighted average according to the PRN specific statistical contributions for each receiver. And continuing on, when receiving the representative signals from the distant sites, the PDC then compares its regionally representative sample as well as the signals preliminarily determined to be spoofed. Thus, for both sets, the PDC performs pairwise cross correlations for each satellite PRN and aggregates and filters the results with a narrow averaging window to reduce variability in the statistic. At this point, the PDC has computed the final spoofing statistic for both sets of signals. For the receiver collection initially determined to be authentic, if the final statistic lies above the secondary threshold, then we confirm the authenticity of the collection of receivers in the local network. Otherwise, if it falls below, then we consider this indicating a poor signal match of the collective signal with that of the other distant sites. We determine these receivers to be spoofed in a coordinated manner. And similarly, for the receivers that initially failed the preliminary check, if the final spoofing statistic is above the secondary threshold, indicating a strong signal match of the GPS signal of these receivers with those of the distant network sites, we conclude that the received signal is in fact authentic. Otherwise, if it again falls below the secondary threshold, then we confirm the lack of authenticity of those receivers. So now we'll discuss some of the implementation details for incorporating our spoofing detection algorithm into the power grid network. So for each PMU, to have its signal processed and evaluated for spoofing detection, it must send several key data items to the central station. In particular, the PMU will send a fragment of its raw GPS signal, along with the receiver tracking parameters, such as which include the Doppler frequency and the carrier phase estimates for the satellite, for the signal from each satellite in view. And these tracking parameters are continuously monitored by every GPS receiver. And by providing these parameters as well, the PDC, or the central station, can condition the raw GPS signal and extract the quadrature phase signal component containing the downsampled version of the encrypted military signal. And each PMU can send this data through these secure NASPnet communication links. For each GPS signal sample we wish to authenticate, the PMU sends a data block made up of individual data packets, where each packet includes a header with information such as the PMU ID, the time of transmission of the signal that's being sent, which is to be authenticated, as well as the packet ID, which helps the central station recognize if a packet has been dropped. Additionally, the header contains some information about the data content for within the given packet. And each data frame within the packet, which has the bulk of the data being sent, will have a frame ID as well as a series of bits and then a corresponding checksum to ensure accuracy of the data sent. To reduce the communication bandwidth requirements, we have each PMU simply send its raw GPS signal along with the scalar tracking parameters, and then we can utilize the processing resources at the central station to generate the conditioned signal samples for each of the received satellite signals. And this significantly helps to reduce the bandwidth requirements for the communication network to send just the raw signal instead of preconditioning and sending all of the signals for each satellite. And we also have here a list of factors that influence the overall bandwidth requirement, along with the values that we chose for our experimentation and the results that we present in the upcoming slides. In particular, the factors that have the largest influence on the bandwidth are the length of the signal fragment, the sampling frequency, and the resolution of the data, as well as the desired rate of authentication. And for a desired rate of about 1 check per minute, which is a value we got after speaking with industry members, with our implementation, the bandwidth requirement is only about 23 kilobytes per second. For the future power grid network, where many of the communication links will be replaced by fiber optic cables, this corresponds to less than 1/1000th of a percent of the total available bandwidth.
Hi. So moving on to the next segment in our implementation section, we will talk about evaluating the spoofing risk, which is associated with each PMU in the network. For this, we considered 4 signal characteristics. The first one is the pseudo-range residuals. So given that the PMU, the power grid is a static infrastructure, we can pre-compute the known positions of these receivers, which can be used to calculate the expected pseudo-ranges. And by computing the difference between the expected and the measured pseudo-ranges, we evaluate the summation of the squared differences across all the satellites. And this test statistic should, in an ideal situation, should follow a chi-square distribution. Any deviation from this chi-square distribution leads to some insights into an anomaly, and this is used to compute the probability of spoofing risk given the pseudo-range measurements or residuals. The next aspect is observing the differences in the clock residuals. So in this particular test statistic, we compute the difference between the clock residuals across 2 time instants, and then compare this with the local oscillator and the difference in their estimated timing. This gives us, this is compared against a Bernoulli distribution with a predefined threshold. The third aspect that we are monitoring is the SNR values. Given that the spoofer transmits the powers at a higher power requirements, therefore any variation in these SNR values can be are monitored using an empirical distribution, and any deviation from this distribution also gives insights into the probability of spoofing risk for given the SNR values. Now, in this particular empirical distribution, we considered 25% under the tail as high fault regions. And the fourth and the final aspect of our spoofing risk implementation is to consider the prior or the historical data about the spoofing risks at each of these PMUs. So by considering a weighted average of these past data with higher weights given to the most recent measurements, we can gain an historical observation on how reliable this PMU has been over time. By combining all these aspects into our spoofing risk evaluation, we calculate the current estimate of the spoofing risk. And this estimate can be also incorporated in the communication protocol that we've described earlier, in order to, which can be later sent to the PDC for further evaluation. Now, the North American power grid infrastructure currently has over 2,500 PMUs, which are spread all over the US. Given this, this brings us to the third aspect of our implementation section, which is to compute the optimal subset of PMUs that needs to be cross-checked in order to constrain or limit the computational load at each PDC. This is calculated by optimizing the cost function, which is shown in this slide. In this, we consider two aspects. One is the individual characteristics of each of these PMU, which depends on one, the spoofing risk that we have talked about in the previous slide. Two is the communication link reliability between the two PMUs in consideration. And the third is the physical security at each of these PMUs in the optimization function. The second aspect is across the PMUs, the reliability characteristics, where we have considered the distance or the physical distance between the two PMUs considered in the cost function. So larger is the geographical separation between the PMUs, lesser is the likelihood that both of them are simultaneously spoofed. Given this, this completes our algorithmic section. To give a brief summary, we've talked about how the GPS works, and we have talked about the hybrid network architecture that we have implemented in our algorithm. Then we talked about our spoofing detection approach, which consists of pairwise check and preliminary statistic computation, and later cross-correlation across the regionally representative snippets. And we've also touched upon the implementation considerations, which include communication protocols, spoofing risk, and subset selection. Now moving on to the next step, which is the experimental results. For this, we have recorded GPS signals during a government-sponsored live spoofing event, which took place in a western US state. And simultaneously, we have also recorded data at 3 other sites in the North America, which are at Illinois, Ohio, and Colorado. For our experiments, we have also recorded data at 3 other sites in South America, at Peru, Pachon, Chile, and Tololo, Chile. For our experiments, based on the bandwidth considerations that Tara has touched upon before, we've considered a sampling rate of 2.5 megahertz and a raw snippet of length of 500 milliseconds, which is later used for cross-correlation. We processed our data using our software-defined radio platform, which is developed in our lab, known as the PyGNSS. Now, let me talk about the initialization stage, where we have analyzed a few minutes of the preliminary statistics computed from both North American and South American regional networks. And based on this, we created a histogram for both authentic data, which is represented by the blue color, and the spoof data, which is represented by the orange color. We represent these histograms using a gamma distribution based on the similarity, and empirically estimated the corresponding parameters, which are listed in this slide. Therefore, we computed the preliminary, thereafter we completed the preliminary threshold by computing the intersection point of these two distributions. We chose this in order to minimize both the probability of false alarm and also probability of misdetection. During testing later on, if our preliminary statistic lies below this threshold, we consider this receiver to be authentic, and if it's below, it is more likely to be spoofed. With this idea in mind, we've computed the preliminary spoofing statistic for all the PMUs in both the networks separately. So in the first network is the US network, which consists of four stations, but one is Western US state, one is Illinois, Colorado, and Ohio. The magenta dotted line represents the threshold, which we have calculated from our empirical distribution. And therefore, for this North American regional network, we observe that our algorithm accurately estimates the Illinois, Colorado, and Ohio to be authentic based on the preliminary test statistic, which lies distinctly above the threshold that we've determined. However, the Western US state, which has been spoofed, lies consistently below this threshold, indicating that it might likely be spoofed. Now, following the same procedure for the South American regional network, that is at Peru, Chile, Pachon, Chile, and Tololo, Chile, we can observe that all these metrics also distinctly lie above the threshold, indicating that the preliminary spoofing status for all these receivers is likely to be authentic. Now, after evaluating the spoofing preliminary status for each of these PMUs in the network, we now move on to create a regionally representative snippet, one for the North American regional network and one for the South American regional network. This is created by combining the receiver snippets, which have been found to be authentic in our preliminary spoofing evaluation. Similar to the preliminary threshold that has been estimated, we have utilized several minutes of the data in order to represent the distribution as gamma distribution, where the blue again indicates the authentic and the orange color indicates the spoofing. Therefore, we again choose our secondary threshold based on the intersection point of the spoof data and the authentic data. Now, moving on, we validate the preliminary state. To validate the preliminary secondary spoofing status of each network, we apply this threshold, which is represented by gamma distribution and is indicated by the magenta dotted line. So when we compare our US representative snippet from North America with the South American representative snippet, we observe that this preliminary secondary statistic lies much distinctly above the threshold, indicating that all these receivers in that representative snippet are indeed authentic. Whereas when we compare the Western US state with that of the South American regional representative snippet, we can see that this lies below the threshold, confirming that our preliminary spoofing status, that this Western US state is indeed spoofed at all times. Now, to summarize, in this talk, we proposed a hybrid architecture to detect spoofing at each PMU in the network, and we also provide a defense, thereby providing a defense against coordinated attacks on regional networks. And thereafter, we also use a regionally representative snippet in order to reduce the overall computational load and bandwidth requirements. We have demonstrated that our algorithm successfully operates on a wide area network to recognize or detect the government-sponsored spoofing attack. And we have, for this, we have also utilized the wide area network of PMUs and two regional networks. And we have not only detected the signal manipulation on the victim receiver, but also simultaneously authenticated the reliability of other receivers in the network. Now, we would also, finally, we would like to thank Professor Jade Morton and Mr. Steve Tyler for collecting the data at Peru, Chile, Colorado, and Ohio sites. And we also would like to thank our lab mates, Craig, Arthur, Matt, and Kara, for assisting with the experimental setup and data collection at the Illinois website and Western US spoofing location. Thank you, and we are open to questions.
What's the timeline you expect to be able to detect that signal has been spoofed?
So we're currently also simulating the latency using.
This is done after the fact, right? This is you record the GPS signal.
Right. This is post-processed.
Use the microphone.
Oh, this one.
Because we've got a call as well. Just hit the button at the bottom of that.
All right. So the question is asking is how quickly do you detect that GPS signal has been spoofed?
Right. So currently, we're also given a communication network structure, we're simulating the queuing processes and the processing and then communication latencies. However, for the NASPnet structure, it's a standard that's been proposed, but it's not currently implemented. So some of these details, for example, the number of servers available at the central processing stations, or the number of the characteristics of these servers, like how quickly they can process data, are not determined. So, but our simulation, given a communication network, will simulate that, the latencies.
Right. So one more thing to add over here is that based on the requirements stated by the power grid community, the desired rate of authentication needs to be like 1 per minute. And even while processing, and given our hybrid architecture where we can use the local PMUs to authenticate first and then go to like distinct sites. So this provides us different layers to realize the spoofing status based on the different latencies that we will encounter. Yeah.
And I'm sorry, can you explain a little bit what you mean by this authenticating once per minute? I'm not really a PMU expert, but I'm kind of trying to understand what's going on here.
Yeah, no. For a spoofer to spoof a receiver effectively, it has to gradually first take control of the receiver's tracking loops, and then it has to, because the tracking loops, if it moves too quickly, the tracking loops will lose lock, and then you'll detect something like jamming. It'll interfere with the authentic signal, and so you'll detect some anomalous behavior. So if it wants to be stealthy, it'll have to slowly move away from the authentic signal peak before it can broadcast the spoofed signal that it wants to send. So in this sense, it takes time. As long as you're tracking the GPS signal, it'll take time for the spoofer to effectively commandeer your tracking loops. So you don't have to check real time continuously the GPS signal you're receiving. You can just check at some periodic rate and a smaller signal fragment. And in that way, you can also reduce on bandwidth requirements by not sending all of your GPS data and just picking a small fragment periodically.
And what does a PMU do if it detects spoofing? Does it I mean, you obviously can figure out that something is wrong, but do you just rely on an internal time source, or what?
Right. So they also have they have atomic clocks that get updated by GPS periodically. So in that case, once you detect that the GPS signal you're receiving is inauthentic, then you would not use that signal to update, because the updating is giving you that clock bias for your inertial clock. So then you would just rely on the drift parameters of your inertial clock, which I think for the updated system, they're supposed to be quite small.
Just to add on to that, right, so if the spoofing is going on for a shorter duration, then we can totally rely on the local oscillators to go on. But if it goes for a longer duration, our lab has also been working on different spoofing mitigation frameworks and also spoofer localization frameworks, where you can detect where the spoofer is, what are the characteristics, so that you can either report to the authorities or kind of take some countermeasures in the long run. Yeah.
So I wanted to ask, back on your slides about
Use the mic.
yeah, sorry. So on your slides about the South
Didn't work. Oh, it's okay. Anyway. Sorry about that. So on your slides about the South American region, the data that you guys acquired from Peru was significantly closer to the preliminary decision threshold than anything. Like the U.S. was very well tracking, but Peru showed some deviation, was much closer to the decision threshold. Did you guys ever figure out why that was?
You're saying that the preliminary statistic was closer to the threshold than the preliminary statistic of,
If you go to the slide with the South American
Right,
preliminary,
right.
yeah. Yeah.
I think it's,
think
for the
also-
receiver noise.
Yeah, I
And
think
also
that-
this is a satellite in common, and because Peru is in quite far away, so that could be a low elevation satellite.
So,
You can
Could it also be because the military channel for Peru might be different from US, so the correlation distribution itself is shifted?
this one is actually preliminary statistics, so it's done within the regional network itself. So, but I agree that the receiver noise that we observed for these sites was significantly higher than the US sites, which might be one of the reasons.
yeah, no, that's a good question. We'll look into that.
Yeah.
So, thank you for the presentation. I had a question on how the threshold was determined. So, the way the threshold was determined was you plotted the distributions for the statistic, and you did it for the duration for which the signal has been collected. Can the threshold change over time, is my first question. And if it does, then how frequently would you want to update it?
Right. So thank you for the question. That's a good point. So right now we have done the threshold determination during the initialization stage, and then we've used the same threshold. And yes, the threshold will change over time because it depends on different characteristics like the spoofing characteristics and the authentic signal receiver noise and distance between the sites and everything. So we haven't actually done analysis about how frequently we need to determine this threshold. Given the spoofing data sets that we had were like 10 minutes long. So, but for this duration, it was determining it at the initialization stage was sufficient. But we will definitely look into how long is this going to be valid. Yeah.
Yeah, we have a question from online from Dan Brancaccio, Chair of the NASP Data and Network Management Task Team. He says, NASPnet doesn't exist. It was a concept that was never implemented. There are some wide area networks where synchrophaser data is shared. Will this work for architectures where the PMU and PDC are both in the same physical location? Or does it need to compare signals from a wide area? Does the PDC require accurate GPS clock? Most control center PDCs run on Windows servers where accurate time of day is difficult to achieve.
So NASPnet is just a standard that was proposed and it's not implemented. The phaser measurement units have been installed, but a network for the future smart grid to have communication transfer throughout the network is still not fully connective. It's still being installed. So we were considering for an architecture like NASPnet overlaying where you have that kind of hybrid architecture, how you could do spoofing detection in a more efficient manner by and compare with a larger number of receivers without directly comparing with all of the receivers. So can you repeat the other sub-questions?
Yeah, will this architecture work where PMU and PDC are both in the same physical location, or does it need to compare signals from a wide area?
Right, so the key, the key for our multi-receiver algorithm is that you have receivers that are dispersed enough such that they can't be, so for the regional network, the receivers should be dispersed enough, just the PMUs. The PDC just processes the data, so we're concerned more about the GPS receivers that we want to authenticate. For for the regional network, the receivers should be far enough apart such that a single GPS, a single transmitter cannot spoof two receivers at the same time, which is not too large of a requirement, since within that would be about maybe 10 kilometers, or it's not. But then for the when we compare with the more distant networks, we're considering maybe a case where you have a coordinated spoofing attack. So you have multiple transmitters spoofing the region in a coordinated manner, and in which case you would see similarities with each of the, you would see similarity in the quadrature phase channel with each of the receivers that are spoofed by that networked attack. But then when you compare with more distant sites, when you compare a condensed version of that signal with more distant sites, then you would see differences. So in that sense, we kind of take advantage of the wide area, the continentally wide area of the power grid network.
Okay, and the final question from him is, does the PDC require accurate GPS clock?
So the PDC just gets the raw GPS signal, the data from the PMUs, and then processes it, and then sends back the decision. So it doesn't have to be equipped with GPS or a precise clock.
Here we have a question from Christopher Hannon. What exactly enforces that the distributions don't overlap? Is this because of the specific provided spoofing data or due to the detection algorithm?
So the key, the reason that you have such good separation between the two distributions is because of the statistic we chose, which looks at the correlation peaks with all of the pairwise checks that you make for each receiver. So when you aggregate, if your receiver is spoofed, you have very small contribution of similarity for the pairwise statistics. So when you're aggregating, the overall result will still be quite limited. Whereas if you have strong correlation peaks, you have much larger pairwise statistics, and aggregating across your network will result in a larger statistic overall. And that's why you get the separation between the two. Or did that answer the...
Yeah, another thing to add is I think it also depends on like the length of the raw snippet that you're considering, the sampling rate that you're considering, which affects the correlation peak value, which will also be reflected in the mean of the distribution and the separation between the distributions. So yeah, that also will affect later on in like the probability of misdetections and false alarm rates as well.
There's a question from a Ken. Do the spoofed signals include the military signals?
So if the spoofer is generating the signal, it cannot also generate the military signals with the encrypted key, unless it has access somehow to the encrypted key, but those are very well guarded.
Christopher Hannon had another question. What spoofing qualities will contribute to the greatest impact into the grid control? In other words, 5 cycles, what impact would occur?
Can you repeat the question?
What spoofing qualities will contribute to greatest impact into the grid control? i.e. 5 cycles, what impact would occur?
I think,
You had it on very early in your intro slide. This answers the question.
Maybe when it is spoofed, there's a time offset, and then
Yeah,
generator to trip, you mentioned that earlier.
Yeah.
I see.
One more forward, maybe?
I see. So there's a standard, can you go one forward? Yeah. So there is some requirement for how accurate the timing needs to be for the PMU devices. It's an IEEE standard of, it has to be accurate within 26 microseconds. And in Daniel Shepard, in this article in GPS World, he looked at he looked more in depth as to what timing inaccuracies would possibly induce a generator to trip, and then I guess I would refer maybe to that article.
Something to add over here is I think the 26 microseconds is more from a monitoring perspective. I think the question was about control perspective. So that might also depend upon what kind of critical bus you are monitoring and what is the timing. So in this paper that we have referred as like literature survey paper, so there they use like an on-off control where if it's above the 26 microseconds, you assume that the generator is stripped, but that might not be the case in like actual power systems. So I think it will depend on the power generator or like the critical bus that you're monitoring to see if it strips or not.
Sorry, are we? Okay. So you mentioned on the bandwidth slide that you expected a lot of these smart grids to have very high bandwidth, i.e. fiber optic. It doesn't seem to me like the timing of that communication line is a big issue. So since a lot of these are really remote, would this work on like a cellular backend if it just had like a CDMA communication with high latency?
That's an interesting point. I guess I'm not sure how secure maybe those networks are, but that's a really good idea, actually. Yeah.
You can talk about this 20-stream PV, and that still works with the existing.
So the current, I guess, I forget what the exact current, so even with the current communication network structure, which has a bandwidth of, I think it depends on depending on which station you're at. But when talking to industry representatives, they gave us a percentage of how much available bandwidth they have in this with our implementation with some of these parameters that you see, and assuming that rate of one check per minute, well, given that they wanted it at one check per minute, a bandwidth of 23 kilobytes per second, even with the existing communication structure, is still just takes up, I think it was like 10-12% of the available bandwidth, not even the used part, for the current communication structure too.
There's a comment from an Alan Goldstein. PMUs are not currently being used for real-time control, except in one experiment in the WECC that fails safe, at least for now. There will be no impact from GPS spoofing, but in the future there may be.
Right, yeah, like especially for the future when they want to use these monitoring measurements for real-time decisions.
Looks like the end of the questions. Thank you very much for a great presentation. Really appreciate it.